In this video, I'm going to explain how we can use reactions quotient value to determine whether precipitations can occur when ions of an insoluble salt or insoluble base are present in a reaction mixture. Hey, I'm Digital. If you like my videos, do remember to click on the subscribe button below so that you won't miss any notification as I update my channel. Reactions quotient Q could be used to determine whether precipitations can occur when ions of an insoluble salt or insoluble base are present in the reaction mixture. For example, silver chloride insoluble salt is only slightly soluble in the aqueous solution and dissociates slightly to give the cation silver ion and also chloride ion the anion. As the dissociation reaction is a reversible reaction, therefore an equilibrium can be reached. When the system is at equilibrium, solubility product expression Ksp could be written as the multiplications of the concentration of the silver ion with the concentrations of the chloride ion. Reactions quotient expression can also be written for this dissociation equation, and the reactions quotient expression is same with the solubility product expression. The difference between solubility product expressions and also reactions quotients is, for solubility product expression, the concentration of silver ion and the chloride ion here are referring to the concentration at equilibrium, while for reactions quotient, the concentrations of silver ion and the chloride ion are the concentration initially before the system reaching the equilibrium. After we get the reactions quotient value, then we can compare the reactions quotient value with the solubility product value in order to determine whether precipitations could occur or not. If the reactions quotient Q value is equal to the solubility product value, that means that the system is at equilibrium and the solution is saturated with the highest concentration of ions in the solutions. When reactions quotient is equal to solubility product, there is no precipitations yet. But if the reactions quotient value is larger than the solubility product value, then the system is not at equilibrium. So initially, the solutions has relatively high concentrations of ions and the solution is supersaturated with ions. Therefore, in order for the system to reach an equilibrium, the system must shift to the left to reduce the concentrations of ions, and this will result in precipitations to occur. When the reactions quotient value is less than the solubility product value, then
the system is not at equilibrium. Initially, there are relatively low concentrations of ions in the solutions and the solutions is unsaturated. To reach equilibrium, the system must shift
to the right to produce more ions. Hence, no precipitations occurs. Now we move on to look at the example questions. Whenever you see the question asking about whether precipitations can occur or not, you must know that the question is asking you to calculate the reactions quotient Q. After you get the reactions quotient Q value, you can then compare with the solubility product value given in order to determine whether the precipitations of the insoluble salt can occur after mixing the two soluble salt together. So like for this question, you are mixing the two soluble salt, lead-2 nitrate and also sodium sulfate together. After mixing, you want to determine whether precipitation of the insoluble salt, lead-2 sulfate could occur in the mixture. How should we tackle this type of question? Step number 1 is to write the reactions quotient expression for the insoluble salt. In this question, the insoluble salt is lead-2 sulfate because the solubility product value Ksp is given for lead-2 sulfate. In order to write the reactions quotient expressions for lead-2 sulfate, first we must write the dissociation equations for lead-2 sulfate. Lead-2 sulfate is an insoluble salt, therefore it only dissolves slightly and dissociates slightly in the aqueous solutions to give respective cation, lead-2 ion and also the sulfate ion. From the dissociation equations, we then can write the reactions quotient expression as product of the concentrations of the cation, lead-2 ion with the concentrations of the anion, sulfate ion. To calculate reactions quotient Q value, we first need to calculate the concentrations of ions that form the insoluble salt in the mixture. So in this question, the insoluble salt is lead-2 sulfate Therefore, the ions involved will be the lead-2 ion, which comes from the lead-2 nitrate solution, and also the sulfate ion, which comes from the sodium sulfate solution. For this, we need to look at how the reactions mixture was prepared. The mixture was prepared by mixing two soluble salt together. Before mixing, the volume of lead-2 nitrate is 100 ml, and for sodium sulfate is 400 ml. After mixing, the volume of the solutions becomes 500 ml. Can you see that here, the volume of solutions increases? This indicates that a dilution process has occurred during the mixing. Therefore, if we want to calculate the concentrations of lead-2 ion in the mixture and also the sulfate ion in the mixture, we must use the dilutions formula M1V1 equals to M2V2. For example, if we want to calculate the concentrations of lead-2 ion in the reaction mixture, we can apply the dilutions formula. M1V1 equals to the molarity and also the volume of lead-2 nitrate before mixing, which is 0.004 molar and 0.1 liter. And M2V2 refer to the molarity and also the volume of lead-2 nitrate after mixing. So M2 we want to find, and the volume V2 after mixing is 0.5 liter. With this, then we get the molarity M2 after mixing equals to 0.0008 molar. And lead-2 nitrate is a soluble salt. In the reaction mixture of 500 ml, the lead-2 nitrate dissociate completely to give lead-2 ion and also the nitrate ion. From the dissociation equation, we can see that 1 mole of lead-2 nitrate will give 1 mole of lead-2 ion in the reactions mixture. Hence, the concentration of lead-2 ion is equal to the concentrations of lead-2 nitrate in the reactions mixture 500 ml, which is equals to 0.0008 molar. The same concept can be applied for sodium sulfate. Before mixing, the molarity M1 is 0.01 molar. Before mixing, the volume V1 is 0.4 liter. After mixing, the molarity M2 we want to find, and the volume after mixing is 0.5 liter. Substitute that into the V2, then we can find the molarity after mixing M2 equals to 0.008 molar. In 500 ml reactions mixture, the soluble sodium sulfate can dissociate completely to give sodium ion and also the sulfate ion. From the dissociation equation, 1 mole of sodium sulfate will dissociate to give 1 mole of sulfate ion. Therefore, the concentration in 500 ml for sodium sulfate is equal to the concentrations of sulfate ion in the reactions mixture, which is equal to 0.008 molar. Then instead number 3, we can calculate the reactions quotients value by substituting the concentrations of the ions into the reactions quotients expression. And for this question, the reactions quotient was calculated to be 6.4 times 10 to the power of -6. Instead number 4, we compare the reactions quotients Q value with the solubility product value to determine whether precipitations can occur or not. For this question, the reactions quotients value was determined to be 6.4 times 10 to the power of -6, which is greater than the solubility product value given 6.3 times 10 to the power of -7. The reactions quotients value is greater than the solubility product value. Hence, the system is not at equilibrium. Initially, because the reactions quotients value is larger, it means that there are relatively high concentrations of ions in the solution. Therefore, the solution is supersaturated. To reach equilibrium, therefore, the system must shift to the left to reduce the concentrations of the ions. So, shift to the left will cause the solid lead-2 sulfate to be produced. Hence, precipitations occurs. In example 2, again, you need to calculate reactions quotients value because the question also asking whether precipitations can occur or not. For this question, 2 soluble salt, silver nitrate, and sodium iodate are being mixed together, and you want to determine after mixing with the silver ion and also iodate ion present, possible for precipitations of silver iodate to occur. To calculate reactions quotient, value, step number 1 is to write the reactions quotient expression for the insoluble salt. For this question, because solubility product value is being given for silver iodate, therefore silver iodate is the insoluble salt. To write the reactions quotient expression, first we must write the dissociation equation for the insoluble salt silver iodate. Insoluble salt silver iodate will have the phase solid, and because only dissociate slightly, so reversible arrows must be used to give the cation silver ion in the aqueous phase and also the iodate ion in the aqueous phase. After we get the dissociation equation, then we can use the dissociation equations to write the reactions quotient expression as the product of the concentrations of cation silver ion and the concentrations of anion iodate ion. In order to calculate the reactions quotient value, we need to calculate the concentrations of ions involved in insoluble salt formations in the reactions mixture. In this question, the insoluble salt is silver iodate. Hence, the ion involved in forming the silver iodate salt is silver ion coming from silver nitrate solution and also the iodate ion coming from sodium iodate. During the reactions mixture preparation, two soluble salt, silver nitrate, and also sodium iodate are being mixed together. Before mixing, silver nitrate solutions is 200 ml. After mixing, the solutions become 1200 ml. And for sodium iodate, before mixing, the volume of sodium iodate is 1000 ml. After mixing, the solutions become 1200 ml. So means that both soluble salt, silver nitrate, and also sodium iodate involved in preparing the insoluble salt has undergone dilutions after mixing. So for this, we can use the dilutions formula M1V1 equals to M2V2 to do the calculations. For example, for silver nitrate solution, before mixing, the molarity is M1, which is equal to 1 times 10 to the power of -4, and V1 is the volume before mixing, which is 0.2 liter, and M2 is the molarity of silver nitrate solutions after mixing, and V2 is the volume of solutions after mixing, which is equal to 1.2 liter. And M2 then is determined to be 1.667 times 10 to the power of -5 molar, and this M2 is the molarity of silver nitrate solution after mixing. Since the silver nitrate salt is a soluble salt, therefore it can dissociate completely in the solution to give the cation silver ion and also the nitrate ion. From the dissociation equation, we can see that 1 mole of silver nitrate dissociate will give 1 mole of silver ion. Hence, the concentration of silver ion in the reactions mixture will be equal to the molarity of the silver nitrate, which is equal to 1.667 times 10 to the power of -5 molar. We can do the same calculation to find the iodate ion in the reactions mixture solution. Before mixing, the molarity of sodium iodate is 1.5 times 10 to the power of -4 molar, and the volume of sodium iodate before mixing, V1, is equal to 1 liter. After mixing, the molarity M2 of sodium iodate we want to find, and the volume after mixing, V2, is 1.2 liter. By substituting all the information into the formula, we then can determine the molarity M2 as 1.25 times 10 to the power of -4 molar. Sodium iodate is a soluble salt, so it can dissociate completely in the aqueous solution to give sodium ion and iodate ion. From the dissociation equation, we can see that 1 mole of sodium iodate dissociate to give 1 mole of iodate ion. Hence, the molarity of iodate ion in the reactions mixture will be equal to the molarity of sodium iodate in the reactions mixture, which is equal to 1.25 times 10 to the power of -4 molar. Step number 3 is to calculate the reactions quotient value. To do this, we just need to substitute the concentrations of silver ion and iodate ion we have found in step number 2 into the reactions quotient expressions to calculate the reactions quotient value as 2.083 times 10 to the power of -9. Step number 4 is to compare the reactions quotient value with the solubility product value given to determine whether precipitations can occur or not. For this question, the reactions quotient value is determined to be 2.083 times 10 to the power of -9. And this value is less than the solubility product value 3.1 times 10 to the power of -8. Hence, the system is not at equilibrium. Initially, there are relatively low concentrations of ions, and the solution initially is unsaturated. Hence, to reach equilibrium, the system must shift to the right in order to increase the concentrations of ions. When shift to the right, more ions are being produced. Therefore, no precipitations can occur in the system. Besides insoluble salt, insoluble phase precipitations can also be determined using the same method. Like for example, in the example 3, the question asks about the precipitations of cobalt-2 hydroxide phase in the solution when the pH of the solution is being adjusted. For this question, since the question asking about precipitation, we are still calculating the reactions quotient Q to determine whether precipitations can occur or not. So basically, in the reactions mixture, for the insoluble phase consists of cobalt-2 nitrate solution, and then the pH is being adjusted to manipulate the concentrations of hydroxide ion in the solution in order to determine whether precipitations of the insoluble phase can occur or not. Step number 1, we still write the reactions quotient expressions for the insoluble base. So the insoluble base here is cobalt-2 hydroxide because the solubility product value is given for cobalt-2 hydroxide. To write the reactions quotient expressions for cobalt-2 hydroxide, first we must write the dissociation equations for cobalt-2 hydroxide. Cobalt-2 hydroxide only slightly dissolve in the aqueous solution, so will only dissociate slightly. Therefore, the phase is solid. When dissociate, giving the cation cobalt-2 plus ion in the aqueous state and also the hydroxide ion in the aqueous state. With the dissociation equation, then we can write the reactions quotient expressions as the product of the concentrations of cobalt ion with the concentrations of the hydroxide ion raised to the power of 2 set with the coefficient in the balanced chemical equation for dissociation reactions. Step number 2 is to calculate the concentrations of ions involved in forming the insoluble base in the reactions mixture. For this question, the insoluble base is cobalt-2 hydroxide, so the ion involved will be the cobalt-2 ion coming from the cobalt-2 nitrate solution and hydroxide ion. To determine the concentrations of cobalt-2 ion, we can determine it from the cobalt-2 nitrate solution. So cobalt-2 nitrate is a soluble salt, therefore will dissociate completely in the aqueous solution to give cobalt-2 ion and also the nitrate ion. 1 mole of cobalt-2 nitrate dissociate to give 1 mole of cobalt-2 ion. Therefore, the concentrations of cobalt-2 ion in the solution is equal to the concentrations of the cobalt-2 nitrate, which is equal to 0.025 molar. To determine the concentrations of hydroxide ion, we can determine it from the pH. We know that pH plus pOH is equal to the 14. pOH therefore is equal to 14 minus 8.6 to give us pOH as 5.4. To calculate the concentrations of hydroxide ion, we must know the relationship between pOH and the concentrations of hydroxide ion. pOH is equal to the negative log concentrations of hydroxide ion. Therefore, to determine the concentrations of hydroxide ion, we just need to equate it to 10 raised to the power of negative pOH, which is 5.4, to give us concentrations of hydroxide ion as 3.981 times 10 to the power of negative 6 molar. In step number 3, we calculate the reactions quotient value by substituting the concentrations of ions that we found in the step 2 into the reactions quotient expressions to give us the reactions quotient as 3.962 times 10 to the power of negative 13. Then in step number 4, we compare the reactions quotient value calculated with the solubility product value given. For this question, the reactions quotient value is 3.962 times 10 to the power of negative 13, which is larger than the solubility product value given 5.92 times 10 to the power of negative 15. Therefore, the system is not at equilibrium, and initially there is high concentration of ions present in the solution. As initially there are relatively high concentrations of ions in the solution, so the solution is therefore super saturated with ions. In order to reach equilibrium, the system must reduce the concentrations of ion by shifting to the left. When shift to the left, we can see that the cobalt-2 hydroxide solid is being produced. As cobalt-2 hydroxide solid is being produced, then we said that the system will form precipitations when the pH is adjusted to 8.6.